Welcome to today's paper reading. Today's paper is titled, MoE-Mamba, Efficient Selective State Space Models with Mixture of Experts. This paper was published on the AR14 preprint by Maciej, Pióro and colleagues from the Polish Academy of Sciences and the University of Warsaw. In the field of sequential modeling, state space models, SSMs, are emerging as strong competitors to transformers. Simultaneously, mixture of experts, MoE, has significantly enhanced transformer-based large language models. The authors propose combining SSMs with MoE to unlock their scaling potential. They demonstrate this with MoE-Mamba, a model that outperforms both Mamba and baseline Transformer-MoE. Notably, MoE-Mamba achieves the same performance as Mamba in 2.35 times fewer training steps, while maintaining the inference performance advantages of Mamba over Transformer. Figure 1 illustrates the log perplexity trends throughout the training process for three models, Mamba 100M, Transformer-MoE 100M, and MoE-Mamba 100M. The graph shows that MoE-Mamba 100M achieves comparable performance to Mamba 100M but requires significantly fewer training steps, demonstrating its efficiency. This comparison highlights the effectiveness of integrating mixture of experts with Mamba architecture. Large language models, LLMs, have become a cornerstone in the AI revolution, primarily due to the transformer architecture and extensive training on internet-scale data. However, questions remain about the exclusivity of transformers and the potential for further scaling. State space models, SSMs, have gained attention for their linear time inference, parallelized training, and strong performance in long-context tasks. The mixture of experts, MoE, approach allows for increased model parameters with minimal computational impact, enabling efficient scaling to trillions of parameters. In this paper, we introduce MoE-Mamba, combining Mamba with a mixture of experts layer to enhance efficiency and scalability of SSMs, potentially competing with the largest state-of-the-art language models. State space models, SSMs, are a family of architectures used for sequence modeling, combining elements of RNNs and CNNs. Despite some identified issues, recent advancements have made deep SSMs competitive against transformers. Mamba, in particular, has shown impressive results with its selective mechanism and hardware-aware design. Additionally, various attention-free architectures have been proposed. Mixture of experts, MoE, is another class of techniques that allow for increased model parameters with minimal impact on computational requirements. MoE models benefit from sparse activation and have been applied in NLP. The MoE-Mamba architecture, introduced by Antoniak et al., connects Mamba with MoE, validating the potential of this combination. The MoE-Mamba model combines the strengths of the Mamba architecture with a mixture of experts, MoE, layer. Mamba, a recently proposed SSM-based model, achieves transformer-like performance by employing a work-efficient parallel scan and reducing memory requirements. The MoE layer, based on the switch transformer design, simplifies previous MoE approaches by setting top K routing to K equals 1, ensuring efficient expert selection. In the MoE-Mamba architecture, Mamba layers and MoE layers are interleaved, allowing for both efficient sequence context integration and conditional processing by the most relevant expert. This design also explores parallel execution of MoE and Mamba layers, inspired by other parallel models, although it yields slightly less effective results compared to the interleaved approach. Table 1 provides a detailed comparison of various model architectures, focusing on the number of parameters and active parameters per token, as well as the final log perplexity and speedup over a vanilla Mamba during training steps. The models compared include Mamba, MoE-Mamba, Transformer-MoE, and Transformer, with specific data provided for 25M and 100M models. The table highlights that the 25M models were trained on approximately 10 billion tokens, while the 100M models were trained on around 30 billion tokens. It's important to note that the parameter counts exclude embedding and output layers, and the differences in total and active parameters are considered insignificant for the results. Figure 2 presents a visual comparison of different architectural designs in sequence modeling. Starting from the left, it shows the vanilla transformer, followed by the Transformer-MoE-Mamba, and finally the MoE-Mamba. The MoE-Mamba architecture is characterized by the interleaving of Mamba layers with MoE layers, which allows for both efficient sequence integration and selective application of expert parameters. This design contrasts with the unconditional processing of the vanilla Mamba and the conditional processing typical in MoE-based models. The empirical validation of the hypothesis that interleaving Mamba with mixture of experts, MoE, can improve performance is demonstrated through significant results. Specifically, MoE-Mamba requires 2.35 times fewer training steps to achieve the same performance as Mamba. This speed-up is crucial for efficiency. The training setup involves comparing MoE-Mamba to three baselines: Mamba, Transformer, and Transformer-MoE, all of which are decoder-only models. The experiments are conducted on the C4 dataset for the next token prediction task. Key design choices include the expansion factor E, which influences the number of parameters and flops, and the management of active parameters to ensure computational feasibility. These factors are essential for maintaining performance while optimizing computational resources. Figure 3 illustrates the parallel MoE-Mamba architecture on the left and the Mamba block on the right. The outputs of the gate and CONV projections are scaled by the expansion factor E, which determines the size of the vectors operated on by CONV and SSM. Vanilla Mamba assumes an expansion factor of E equals 2, as proposed by Gu and Dao, 2023. This expansion factor is directly proportional to the number of floating point operations, flops, and parameters in the Mamba layer, influencing computational efficiency and model complexity. Table 2 provides a detailed comparison of various ratios of parameters between Mamba and MoE models. It highlights that the total number of parameters across all models is fixed at 542 million, with 26 million active parameters per token. The table also outlines the expansion factor E for the Mamba layer, which is crucial for understanding the distribution and efficiency of parameters in these models. Figure 4 illustrates the smooth training loss, measured in log perplexity, for MoE-Mamba models with varying numbers of experts and approximately 26 million active non-embedding parameters. The data clearly shows that as the number of experts increases, the final log perplexity improves in a monotonic fashion. This trend indicates that MoE-Mamba scales favorably with the addition of more experts, with the best performance observed at 32 experts. This finding suggests that increasing the number of experts could potentially yield further performance gains. Table 3 presents a comparison of various MoE, mixture of experts, variants within the Mamba architecture, focusing on their final log perplexity scores after processing 1 billion tokens. The table includes different configurations such as CONV projection, gate projection, and output projection, among others. Notably, none of the tested variants managed to outperform the baseline MoE-Mamba configuration, indicating its effectiveness. This data suggests that future research should focus on refining the MoE-Mamba model rather than exploring alternative MoE placements within the Mamba framework. Figure 5 illustrates the final log perplexity at various ratios of active Mamba to MoE active parameters. The data reveals that as the ratio of Mamba parameters to MoE parameters increases, the performance improves. However, this improvement becomes marginal after reaching a 3:3 ratio. Ratios higher than this are deemed impractical due to inefficient hardware utilization and increased routing costs associated with a large number of experts. This insight guides the default choice for all other experiments in the study. Table 4 presents the log perplexity after processing 1 billion tokens for models with different numbers of experts. The parameter counts do not include the embedding and output layers. The table shows that models with fewer experts perform worse than the vanilla Mamba. This observation aligns with previous findings that a single expert MoE layer is less effective than vanilla Mamba. The log perplexity values range from 3.72 to 3.67, and the speedup over the vanilla Mamba varies, indicating the impact of the number of experts on model performance and efficiency. Figure 6 presents a comparison of the final log perplexity for different numbers of experts in both sequential and parallel MoE-Mamba configurations. This comparison highlights the performance differences between the two designs as the number of experts varies, providing insights into the scalability and efficiency of each approach. In future work, the authors plan to explore scaling laws for models with active parameters smaller than 1 billion and total parameters up to 2.4 billion. They also aim to integrate mixture of experts, MoE, more effectively into the Mamba layer, potentially through sparse computation, to optimize the model architecture. Additionally, they intend to investigate different types of MoE architectures, such as expert choice routers and fully differentiable designs, to enhance the performance of MoE-Mamba models. In this study, the authors introduced the first integration of mixture of experts with the Mamba architecture, termed MoE-Mamba. This novel approach not only retains the inference benefits of Mamba but also requires significantly fewer training steps to achieve the same performance, specifically 2.35 times fewer. The authors demonstrated that these performance improvements are robust across varying model sizes, training lengths, and the number of experts. Additionally, they explored various alternative designs integrating mixture of experts within the Mamba block, although none surpassed the performance of MoE-Mamba. These investigations, however, were valuable in identifying ineffective research directions and pointing towards promising ones. The work opens a new research avenue by combining mixture of experts with state space models, which the authors believe will enable more efficient scaling to even larger language models. The study acknowledges significant contributions and support from various sources, including computational resources and a supportive research environment. Thank you for watching.